Eddy current testing is a non-contact electromagnetic method, and in heat exchanger work it is the primary tool for inspecting non-ferromagnetic tubing. This selection matrix comes straight from the Olympus Tube Inspection Probe catalog. Non-ferromagnetic alloys: aluminium, brass, copper, hastelloy, incalloy, 300 series stainless, titanium and zirconium go to eddy current. Ferromagnetic carbon steel goes to remote field, near field, or magnetic flux leakage. Get this step wrong and nothing downstream is defensible. The physics is on the left, from that same catalog. A bobbin probe carries two circumferential coils driven with alternating current. Those coils produce an alternating magnetic field. Where that field penetrates a conductive tube wall, it drives circulating eddy currents. By Lenz's law, those currents generate an opposing secondary field, and that opposition is what the coil feels as a change in impedance. On the right is a schematic redrawn from the figure. Drive current, primary field, eddy currents, opposing secondary field. Introduce a discontinuity and the current paths divert, the opposing field changes, and the coil impedance moves. That movement is the entire measurement. Eddy current density is highest next to the coil and decays with depth. The standard depth of penetration is where density has fallen to 37% of its surface value, set by frequency, conductivity, and permeability. So frequency selection is a calculation. The catalog states it directly: F90 equals 3 times resistivity in micro-ohm centimeters, divided by wall thickness in millimeters squared. At F90 there is about 90 degrees of phase lag between a 10% internal groove and a 20% external groove, and the prime frequency is twice F90. This is a standard bobbin probe from the Eddy tubing catalog. Diameter is chosen for fill factor. The probe must fill an optimal portion of the tube inside diameter. The two circumferential coils run simultaneously in absolute and differential bridge mode, giving two different views of the same tube. These are the measured responses printed in the catalog: absolute on the left, differential on the right. Same probe, same defects, same pass. For U-bends there is a flexible bobbin, for mildly ferromagnetic tubing, a magnetic saturation bobbin. Acquisition is disciplined. Balance the probe in a clear area of the calibration standard. Push it the full length of the tube. Start acquisition, then pull at constant speed. The application guide recommends about 300 mm per second, at a standard acquisition rate of 2000 Hz. Stay below 1 meter per second to keep at least 2 points per millimeter. Landmarks: anchor axial position, tube sheet in, the support plates, and tube sheet out. Everything you report is referenced to a matching calibration standard. This is the CT02 extended ASME calibration tube. The guide lists its flaws: a 10% internal groove, a 20% external groove, a through-wall hole, outside diameter flat bottom holes at 40, 60 and 80%, and 4 outside diameter flat bottom holes at 20%. For frequencies are proposed from F90, twice F90, F90, half, and 1/8. By default, calibration uses the whole signal at 1 volt and 40 degrees, on both absolute and differential channels. The lysagus is an impedance plane. Horizontal is resistance, vertical is inductive reactance. Balancing puts the operating point at the origin. Lift the probe and the point runs along the liftoff trajectory. That direction is your reference, and calibration rotates the display so flaw signals sit at a useful angle from it. The chart on the right is a reference figure: a bobbin probe passing an outside groove, inside groove, through hole, steel support plate, magnetite deposit and dent, with absolute above and differential below. Absolute follows gradual change in geometry. Differential compares the two coils, so a localized flaw produces a two-lobe figure of 8, and slow drift is rejected. Depth comes from phase, not amplitude. This is a real phase sizing curve from the application guide, on the differential channel at F1. The 10% internal groove sits at 10 degrees. The through-wall hole at 40. Then 80% at 71, 60 at 99, 40 at 120, and 20% at 140 degrees. Internal and external flaws fall on opposite limbs, hence a dual segment fit. Measure from the liftoff signal to the flaw signal. Reverse the vector and you introduce a 180-degree bias, exactly as the guide shows. This is what it looks like in the field. A Multiscan MS5800 record from stainless 304 tubing, 19.05 mm outside diameter, 1.65 mm wall. Strip charts carry position, lysagus panels carry shape, phase, and amplitude. The absolute 90 channel measures 0.484 volts peak to peak at 166.9 degrees, sized 87% outside diameter. The mixed channel reads 16% inside diameter on the same indication. Support plates are the classic problem. A ferromagnetic support ring can bury an outside diameter flaw. Multi-frequency mixing is the answer, shown here end-to-end on a Nortec 500D is set the prime frequency, 64 kHz, and calibrate the through-wall hole to about 40 degrees. Scan the support and store it as the reference. Set a second, lower frequency 8 kHz and match its gain and angle to the stored reference. Then subtract. On the left, the support at F1, on the right, the mix. The support is largely cancelled and flaw signals survive. A residual support signal is normal, and this technique works for ferromagnetic supports only. Know the boundaries. Standard bob and eddy current is for non-ferromagnetic tubing. Permeability variation, lift-off, fill factor, Denson deposits all generate real responses that must not be reported as wall loss. Bobbin coils are relatively insensitive to circumferential cracking. Array probes exist for that. And where sizing must be defended, internal rotary ultrasound remains the validation technique for any material. Read in a fixed order. Confirm channel and frequency. Locate the indication against a landmark. Judge the shape. Measure phase with the same method you calibrated with average peak on absolute, peak to peak on differential. Only then take a size from the sizing curve. Review filtered and unfiltered data, because median high-pass filters can distort phase. And validate data quality, dead channels, saturation, missing landmarks, before any tube is called clean. Correct technique for the material. Correct probe and fill factor. Correct frequency set. Calibration on a matching standard. And an interpretation you can defend against the reference data. JARESA consultation services. Integrity, inspection, reliability.